Think iOS. And yeah, I think now, okay, Hari and Astrid, or whoever, yeah, I think put it out. I think it's not on. on Power?
Maybe power, yeah.
Okay. That's what happens. Probably input. Okay. Hello, Niranjan.
About the speaker.
I think this has been moved, so you want to move this also. Whatever is readable, I mean, I'm not picky about this. Like you guys use this more than me. So as far as you guys find it readable. Or Niranjan is there, right? Yeah, he should decide what he wants. Readable? Is that readable?
I can read it.
Yeah, he said again.
It is?
I think the speaker is not working. It's only connected to the computer.
Okay. What
The
is
speaker
not-
is not working. I heard it from the computer, but not from the outside.
But there is no outside speaker.
Only the.
I think so.
Okay.
Yeah, because we don't have an audio, right?
Okay.
There was a request for grading the homework. I'll do that very quickly. And I was hoping to do that on Friday, but I couldn't. So I could. I'll do that maybe in 2 days, if not today. So okay. Thanks. And you ask me again. So no, don't hesitate to do it. And oh, and there was one more comment I wanted to make about the quizzes. I think I was being lenient with, so usually there are 2 or 3 quizzes that I ask, and sometimes people just submit one quiz out of it, and I'm typically lenient, but then when it is consistent, I will try to take off points. I don't want to, but that's why I'm warning. And it's just to be fair to everyone. Someone does 3 questions and someone does 1 question. It's just it's a 3 points. So I don't want to take off points. So be consistent. Just don't do it for the sake of it. And what? So we have the midterm exam September 29th, Friday. Now there's a possibility that there will be a 5th homework that will come in and it will be due on the day of the exam. Okay, that's a possibility, but let me see. Okay, that's it. There's a good chance I think that will happen because there's a 1 week of that. So be aware of that. Be prepared for that. It will be due right. It will be after the exam in the sense it will be due in the evening, but the content of the questions will be relevant for the exam. So you won't have feedback for those questions. So that's the chapter. We'll see how it looks. The exam will be in this room itself, and it will start. For now, we are starting at 9:30 unless there is a popular demand to start it earlier. We start at 9:30 and if we go till 10:50. 10:50. So expect 4 to 6 questions. Could be 4 questions or 6 questions. I don't think I'll make it more than that or less than that. No take home part to the exam. Okay. Any general questions or comments? Yeah, I said I will try to give an idea of. Oh, there's a homework also due for you guys, right? Yeah. Okay, change of plans a little because I have to cover the homework. But the last time I did not tell you the polymetrics, right? So I was hoping to finish that and I did not do that. Okay. Yeah, let it keep going. Okay, so we want to have an idea of what quantum mechanics is, how is it different, at least mathematically speaking, how is it different from the standard Newtonian physics? And basic idea would be that, or how do you achieve it? It is usually by upgrading a variable, a physical quantity like momentum, for example, to an operator. And when you think of operator, what you want to keep in mind is it's a differential operator, like derivative, it acts on something. Or it could also be a matrix. So that's the two things you want to keep in. That is how it is practically done. But as far as the algebra goes, it is the idea of a vector that comes into picture. So a vector space is what builds is the basic mathematical tool that you use to interpret quantum mechanics. So I want to give at least the basic ideas that we have learned into this quantum mechanical review. So the notation will be in quantum mechanics. Usually we say Bra and Ket notations, but here we are going to use the simple E basis that we chose and see how that goes on. So let me have a quick quantum experiment. So this is a Stern-Gerlach experiment. What this is you have, let's think of a setup where there is a small volume of gas. That's the way to think of it. Think of it as 1 centimeter by 1 centimeter by 1 centimeter. We want to work with atoms. Atoms are usually quantum mechanical in nature. So we want to somehow work with atoms, but it is very hard to isolate one atom. So often what you do is that you have a beam of atoms. So you take a small, tiny 1 centimeter by 1 centimeter by 1 centimeter volume, then heat it up. So think of it as heating it up and make a small hole. When you heat it up, they all move around. So there are atoms inside this and they all come in all directions, right? So if you make a small hole, they all come in all directions. Make a small slit or a small hole inside a metal sheet, and only those that are moving in this direction come out. And if you make a couple of them, very quickly you have a collimated atom moving with a certain velocity. So you have a lot of atoms. That's how you like 10 raised to 23 of them. They all come out in with a certain velocity. So that's a beam of atoms. We don't work with one atom. We work with a beam of atoms. That's the idea. And what's the property we are interested in? We want to think of a magnetic moment, so mu, is a magnetic moment. And in this case, the magnetic moment of, let's say, the atom that we have, in this case, it could be the silver atoms. So silver atoms, right, Ag. So it could be any atom in principle. Silver atoms are convenient in the sense that has a nice magnetic moment that you can work with. Magnetic moment is, how is it related to any other physical quantity? How do you define magnetic moment? Any idea of an atom, let's say, or let's say, yeah, what do you know about magnetic moment? Anything? Electric moment? What is electric moment? Electric dipole moment? What is electric dipole moment? Define. That you know, right?
The charge times the distance.
So if you keep equal charges, you separate it by a certain distance, you have created a dipole moment. Like for example, an atom, if usually you would, if it was perfectly spherically symmetric, like helium atom, the center of positive charge is pretty much the same as the center of negative charge. But if you have take any other atom, like the sodium atom, the center of the positive charge need not be exactly coinciding with the center of the negative charge. So that's a small distance between them, and that distance times the charge is a dipole moment. So most of the atoms have an electric dipole moment. What is an magnetic dipole moment? Define it.
If you
Huh?
put a charge.
In the magnetic field.
No, it's usually a property, right? Like electric charge, right? Dipole moment did not need an electric field, right? It interacts with it. Maybe that's what it is. An electric dipole moment will interact with an electric field. Magnetic dipole moment will interact with a magnetic field. But what is the property that decides the magnetic dipole moment? If you want a very high magnetic dipole moment, what would you do? Like if you want to have very high electric dipole moment, you will have a very large charge separated by a very large distance. So what is a magnetic dipole moment?
The current.
Current, right? So you would say, define again, yeah, current. What is the magnetic dipole moment? Yeah.
The area.
Area and a current. So typically it is, so the dipole, so this is dipole. Direction. So usually you say this is D, that's equal to charge times the distance, right? The distance is A, that's negative charge, that's a positive charge, and it goes from negative to positive. That's your dipole moment. Right. And now the magnetic dipole moment, mu, according to Aryan, is you have a loop of current. And then it is I times A, so there's an area of the loop. And what's the direction? I times A, area is a loop, what's the direction? You use the right hand rule and it comes out. That's correct, that's good. Okay, but you need a current for this. What if you have a single charge? If you have a moving charge, what is the magnetic dipole moment due to a point charge?
The chart.
Spin of the charge or angular momentum of the charge. Very good. So, like we have a property related to charge here, it is also related to Q. It also depends on the mass. Right? That's because you want to, and it's not really dependent on the mass. It is because you want to write it as angular momentum. There is a mass in the angular momentum. M cancels out. So it is not really mass dependent because that's a way of writing it. And you see a mass in there. Now, what is angular momentum? How is angular momentum defined? Mass times momentum R cross P. That's P is velocity. What happens if you are in the rest frame? of the particle. So the particle is moving around and you sit on the particle itself. So its momentum is zero, right? My momentum in my own frame is zero. So what's the angular momentum I can measure for myself? Should be zero, right? Because velocity is zero, momentum is zero. So R cross P is zero. But that's not completely true. Even when you're in the rest frame, sometimes there is a residual angular momentum, which is called the spin of a particle. So the angular momentum, so this is J. This should in principle be J. And J can be equals to S spin plus L. And spin is a purely quantum quantity and is equal to h bar over 2 times cannot be just h bar over 2. Let's say an electron spin of an electron. It must be something there because it needs to be a vector, right? H is not a vector. What is it there? It turns out to be sigma pi. What did you say?
Sigma poly.
Poly sigma matrix. So this is where the poly matrices come in. So this is a sigma. So this is a poly matrix. But for our purposes, there is a spin which we have to still define. Okay, I'll come to that. But spin has this very non-trivial feature that it is not even a number, or it's not even, it's by construction a matrix. That it is you can this. What is a classical analog of this? The classical, I mean non-quantum mechanical analog of this. It doesn't exist because there is an h bar. Whenever you say classical analog or quantum mechanical analog, you want to set h bar equal to 0. There is no spin in the Newtonian physics. We don't talk about spin in Newton, it's pure quantum mechanical. So that's the idea that we want to get some quantum effect in there. So this is Q over 2m times let's say spin on J. So we want to capture the physics associated with the spin. Spin for our purposes, given an atom, it has a direction, right? Magnetic moment is a vector. So it is a vector which tries to align with the magnetic field. If you have a loop of current, put it in a magnetic field, what does it try to do? It tries to align itself, right? That's what it does. Same thing with atoms. These atoms have an inbuilt magnetic dipole moment in it. If they see a magnetic pole field, they align with it. That's the basic physics of that, and that's what we want to do. So we have a beam of atoms, each of them having a magnetic moment. Their job is to align with the magnetic field. There is no magnetic field inside in here, so they are randomly directed. So if you think of all the atoms inside of this room, they will be all in all random direction. Put that in a magnetic field. So that represents a magnetic field. Not just a magnetic field, notice that I made a pointed sharp object there and a flat object there. That means it's a non-homogeneous magnetic field. So this magnetic field is like this. That's your magnetic field. Maybe another question. So suppose you have electric field lines like this. Right. Let's say there is a positive charge here, and there is a positive charge here, Q1 and Q2. Both of them experience a force. Which one experiences a larger force? Q2 experiences a larger force, and why is that? Because electric field is larger here. There is more lines here. That means the density of lines represents the magnitude of the electric field, larger electric field. So here the same idea, this is magnetic field. So the magnetic field is larger because that's more concentrated, now more number of lines, so there are more number, there's a larger, stronger magnetic field near the tip of the North Pole and smaller at the South Pole. So what is the force that it experiences? Or let's start with energy. Energy is often represented by the Hamiltonian, and that's equal to the interaction energy between a magnetic dipole moment and a magnetic field is mu dotted with B. It's the same as the dipole moment of an electric dipole moment, it is B dotted with E. There's a negative sign, so there should be a negative sign here also. So the magnetic energy associated with the interaction between a magnetic dipole moment and a magnetic field is minus mu dotted with E. Force will be the differentiation of this energy. So force would be negative gradient of the Hamiltonian. That's equal to negative gradient of minus mu dotted with B. Let's choose this magnetic field to be in the Z direction. So the gradient is all in the Z direction. So that's minus C hat d by dz. The way I have shown the picture, it is clearly the gradient is not necessarily in the Z direction, but we can always take a small region where mostly it is in the Z direction. So I'm saying in this approximation here, this I'm saying is mostly the gradient is in the Z direction, so it's plus mu dotted with B. So gradient in Z direction. Just a configuration of that experiment if you want. I can choose the magnetic field itself in the Z direction. So that's equal to Z hat times d by dz of mu times b, which is a function of Z because it has a gradient, and cosine theta. This is the important piece. Cosine theta now is the magnetic field here, and that is mu. Since we said we have no control on the atoms, atom could be pointing in any direction to begin with. That's the angle theta. To begin with, the magnetic moment of the atoms could be at any angle with respect to theta. That's your theta. So you should have the force dependent on cosine theta. So basically, bring in a mu also here, d by dz of p. Idea is there is an angle theta dependence. That means to say that if the atoms are perpendicular to the magnetic field, what is the force they will experience? It should be zero, right? Cosine theta is zero, it should be zero. So that there are a set of atoms which should go and hit straight. So the no force is experienced by that. It should go all the way to zero. If the angle theta was slightly bigger, so angle theta is 10 degrees or something, so it experiences a small force here, experiences a small force here. That's what you expect. So that's large theta. And silver silver atoms, basically you can use that this is what is used in a photographic plate. So you take a simple photograph plate and it should give you a series of points. This is what was expected, right? This is an expected result. But experimentally, what was noticed is that you don't see this all stretched. There are only 2 points. So this is experimental. And that's what we want to try to explain. So our goal is that this is what experiment is. This is what was expected, the whole series. So in a sense, it was supposed to be a straight line. Yeah. Now, at this point, there are various ways of approach. One could say that, oh, we want to explain this. So let's stick to classical view. We are going to do something, whatever we are aware of. But to begin with, we are going to say that to be able to explain this, we have to bring in new machinery, new mathematical tools for that. So we are going to change our description right from the beginning itself. So that's your setup. And what is the what is the tool or mathematical description of this? And we want to use our vector space in here. We have a basis, so let's think of some vector, let's say A. Okay, that's the vector quantity that you're measuring. This could be your mu, right? That's your magnetic moment. And now you're using a magnetic field to project this mu in the direction of the magnetic field, right? There's a dot product in there. And that immediately brings in the basis associated with the B. So we will call this the basis, let's call it E1, and E2, E2. For simplicity, but let's say that there are only two possibilities. The basis has only two vectors, E1 and E2. This is the interaction. That's the magnet. That magnet is deciding that. This is your source. You can say that's your mu if you want. This is mu dotted with B. This is the interaction. But now, what you can do is that this is a setup. I can select this or this. I can either select this piece or that piece. So there's going to be a selection. Let me say I select the top one. And I'll come to that in a minute, what I mean by selection. And once I select this, this is what I get. If I were to get this beam here, this is a basis. So this again, you say that this is a projection. That's E1. So this is going to be the observer. So a simple experimental setup always has a source, observer, there is an interaction, and I brought in a new thing, which is the selection, which is what we will call it measurement. We will try to distinguish between measurement and interaction. Interaction is always there. We don't have too much control on it. Selection means a measurement means you will check something. Is this happening or not? And that's what we will mean by measurement or selection. So let's see how this can be put together into the Stern Gala. That's it. Okay. So the first thing is remember completeness relation. This is E1 plus E2 is equal to 1. That's completeness. Orthogonality means EI dotted with EJ is equal to delta I. And now, so this is orthogonality. There is also the idea of projection operator in here. So let's see what happens if you have a vector A. And I multiply that by 1. That's equal to A dotted with E1. And maybe we want to be careful here, right? So let's say this is 1, 2, right? So on top, maybe the house. So this is E1 plus E2. change the parenthesis a bit. And you say that's one clock. Very simple things, but now we're going to interpret this as A1 E1 plus A2 E2. Let's define projection operators here. Projection operators. And this is what will be called measurements. So when we measure something, this will be projecting the operator in that basis. For example, E1 E1 projected in the direction of A is equal to E1 times A1. And same thing, E2 after the A equal to E2 times A2. So these are projection operators. They project the vector in the direction of E1. So that's the simple idea. So this is a projection operator here. So I have a magnet which should be interpreted as it can either project whatever was there on the source in one basis or in the other basis. If it is already in the basis, that's simple, but otherwise that could be non-trivial things coming in. I want to define probability amplitude. Say, probability amplitude. Of a process. Let's say this is our E1. Let's say and maybe I should also talk about my selection a bit. Then let's say E1 itself. Notice what we are saying is that this beam here could have gone like this or like this, right? There are two possibilities that can happen in the experiment, and you can always come and close this beam. You basically close that. You put a small slit there so that it doesn't go forward. And that's what I mean by selecting. I'm selecting the top beam. All the atoms that are moving upward, I can select it out. And all the atoms that are trying to go down, I can close it down. So that's what I mean by selecting. What that means that from this point on, these are all in the direction of E1 or in the top if it was in that basis. So this is a way of building your E1 if you want. So this is one Stern-Gerlach setup. That's second Stern-Gerlach setup, and that's a third Stern-Gerlach setup. So when I say that this brings you to, the whole setup is built out of Stern-Gerlach setup. Which means to say that in the beginning, I have a completely incoherent beam. I have all the atoms in all directions. But down here, all the atoms are coherent. They are all in the direction of the magnetic field. Or at least they align. If I were to put another Stern-Gerlach setup, again, they will all be in the same direction. So this is a way of selecting whatever it means by this dot. It doesn't necessarily mean that it is all in the direction of the magnetic field, because they might be making an angle. Remember what happens to a dipole moment in the magnetic field, classically speaking. So that's your mu. There are two things. It tries to go around the magnetic field. It spins around the magnetic field. That's one thing it happens. And the second is there is a force. We talked about a gradient of force. So if there is a gradient of the force, it drifts. So one is a drift, and the second is the precession that is happening in the magnetic field. That's a classical picture, but overall, there is this dot, which often we will say that it is aligned in the magnetic field, but not necessarily aligned, it is all in the top cone of the magnetic field. And this is the second one, and you can pick that. And that's this. So this is one Stern Gerlach setup. So this is SG setup. From there, you do a magnetic field again, another setup here. And then this is the third setup. So every time I say that, oh, I'm choosing a basis vector, it's basically I'm bringing in a Stern Gerlach setup, a magnetic field. So every time I have to pick something, I have to get a magnetic field associated with it. With that picture set, now what is the probability amplitude associated with this? Probability amplitude, this is not probability, probability will be square of the probability. That will be, if this is the process, we will say it is E1, take a dot product of E1 times E1 and dotted with E1. So notice there is a projection operator here. It is projecting with the source on the left. It's projecting with the observer on the right. In this case, this is simply E1 dotted with E1 times E1 dotted with E1, that's equal to 1. Which makes sense. You're saying that all the atoms are aligned with the magnetic field here. You put a magnetic field again, nothing should change. All that are aligned should come out. Right? The same, it's like a polarization problem, right? If all the atoms are polarized in the up direction, you keep a magnet which selects between up and down. They're already up anyway, so all of them are selected, that will go through. On the other hand, if I were to do the second process, so this is, let's say, 1, probability amplitude of 2 would be E1 dotted with E2. E2 with E1, that will be equal to E1 dotted with E2 times 2 with E1. That's equal to 0. E2 dotted with E1 is 0, which is understandable. I selected only the top beam, but no, now I'm doing a slightly different form, right? So this is the selection now. I changed it. If I were to select the second one, that's my beam. And this time, since I'm selecting the second one, all of them are in the top direction. The magnetic field will not be able to select the bottom. So it's orthogonal. So it is 0. So that's a simple idea, but this quickly changes. If you want to see non-trivial features, you want to see when the magnet is not in the same basis as your source or observer. Let's say this can be G1. And this is G2. What we're saying is that the magnetic field is in a different basis than your source and observer. That's your E2. And G1 and G2 could be in a different basis altogether. In general, in any basis. That's your G1. And that's your G2. Let's say for concreteness, this is angle theta. That's just a choice I made. And I do the same selection again. Think of polarization problem and it will help you interpret this. So you have a beam which is polarized in the E1 direction. Now I'm using a magnet where I want projection along this direction and projection along the G1 direction, and then I observe it eventually in the direction of E1. So what's the probability amplitude of selecting this? So, so that will be equal to E1 dotted with G1 dotted with E1 again, that's equal to E1 dotted with E1 times G1 dotted with E1, and that's equal to E1 dotted with G1 is cosine theta And there are two of them, so it's cosine square. Theta. If the angle was 45 degrees, then you would say, so this is probability amplitude, so probability itself. This is probability. Is equal to P, which will be the square of the probability amplitude. If it is a complex quantity, you have to make sure it's a magnitude of that. So that's equal to cosine 4 theta. You might suddenly want to understand, oh, why is that a cosine 4 theta? I mean, remember that probabilities have to add up to all to be equal to 1. So how does the probability come to equal to 1? So let's very quickly go through this whole possibilities. And the possibilities will be, so we can, let's keep the source the same. And the magnet also to be in the same direction. Let's E2. So magnet is fixed for the second setup, right? So there is a first setup here that selects, the second setup is fixed. The selection process is what I change. Do I choose the top or the bottom? Okay, that's it. That's what I can change. And this one also I can change. So this is the observer. So let's say these two are the possibilities where I change. So that's the first situation. So let's say 1. Second one is keep the beam the same. One, 2, same, and keep this also the same, but now I look for the components that are in the second direction. Third, 4 possibilities, right? So let's E1, keep this the same. Magnet is being kept the same. E1, 2, 2. That's G1, G1, G2, 2. Magnet and the source are being kept the same. Now I changed my selection and I select the top part. When I select the top part, I have 2 possibilities which I can measure. I can either measure it in the direction of E1 or in the direction of E2. Notice the only thing I'm doing is basis vector change, right? I bring something in, project it in another basis, and then do the measurement in the old base. Right? That's the trick I'm using, and we will see that these effects are going to be non-trivial almost immediately. In a sense. So, what is PA? Probability amplitude. Project this E1, that's a top selection, E1 dotted with G1, G1 dotted with E1. That's E1 dotted with G1 times G1 dotted with E1. That's what we did. That's cosine square. Probability amplitude here. E1 dotted with G1. That's the same, but now G1 is being selected, and then you got it with E2. This is now different. E1 dotted with G1 is cosine theta, but G1 dotted with E2 is sine theta. Right? 90 minus theta cosine of 90 minus theta, that's sine theta. If it was 45 degrees, that would be cosine square, so that's 1 by 2 and 1 by 2, and this probability will be cosine 4 theta here. Probability here is cosine square theta, sine square theta, and again do the same thing. This is E1 dotted with E1. This time we are selecting the bottom, so it is 2. Select the second one, so it is G2 dotted with 1. E1 dotted with G2, E1 dotted with G2, so it's 90 plus theta cosine of 90 plus theta is minus of sine, minus of cosine theta itself. And G2 dotted with E1. G2 dotted with E1. Oh, it's the same, is it? Yeah. Yes. Okay, E1, did I do this correct? E1 dotted with G2, G2 dotted with E1. E1 dotted with G2. E1 dotted with G2 is the sine of 90 plus theta, right? That's sine.
Sine, yes.
The sine of 90 plus theta is sine theta, right? So it's minus sine theta, minus sine theta, right? The sine of 90
Plus
plus,
sign, I think it's plus.
the sine of 90 plus theta is sine,
Plus.
minus even here, right? Or is it plus? You're saying plus?
I think plus.
Okay. Okay, so the sine of 90 plus here, I mean, this is the curve, right? So the sine function is like this, right? So let's say that's your angle theta. 90 plus theta is here. So that will be identical to here, so it is the sine of, I would say it's minus, right? Just because it's to the bottom. So
Yeah.
I think it's minus, and it's minus sine theta, so that's minus sine theta and G2 dotted with E1. That's the same thing, right? Is that correct? Okay, okay, maybe, yeah, that's sine square theta, okay. So E8. I recall it's supposed to be slightly different, but we'll see.
Plus sign.
E1, huh? This is sine square, right?
Plus sign is one.
Because it's square, yeah, square. So yeah, that's okay, I guess. I think maybe I wrote this down here. So this is E1 dotted with G2 and G2 dotted with 1. G2 dotted with G2. What is E1 dotted with G2? Again, the same, so it's minus sine theta. So what I'm looking for. G2 dotted with G2. If this is theta, that's theta. That's the sine theta, yeah, okay. I think this is the term I was looking for. Right? So probability here is sine 4 theta. And probability here is again the sine square theta. Sine square theta. Often when we see this cosine 4 theta, we suddenly wonder that, oh, is the probability really adding up? And these are all the possibilities, right? If I keep this fixed, the magnet fixed, and only the selection process is being changed. This is, remember, a measurement. I'm looking into what happened. So if I only put the freedom in the measurement and the observer, there are 4 possibilities. So all this should be equal to 1, because the total probability should be equal to 1. And that is indeed equal. So total is equal to, if you realize that cosine square theta plus sine square theta is equal to 1 squared. That's 1 to begin with. So if you square it, you get all the 4 pieces. So this is cosine 4 theta plus sine 4 theta plus 2 times sine square theta cosine square theta, which is indeed equal to 1. That's just a verification that all this does go through. But now, what can we, where is the quantum effect in here, or when you really see this as a measurement, what is actually so non-trivial about this? So let's actually do following. This is an interpretation now.
Oh.
Question.
Oh, no, the other one.
Oh,
It's okay.
I did all this. So you're so behind. But the recording might help.
Yeah, it's YouTube.
Okay.
Okay.
Okay, so this is what we will call measurement. Disturbs the system. A very popular statement, often been thought of as a Schrodinger's cat problem, if you want. If you look into whether the cat is alive or dead, then you have changed the system. Or more recently in the quantum information era, this is also called the no cloning theorem. Same idea. The idea is that if you look at it, so it's like a password. If you have a password, by definition, you don't want anyone to look at it, right? So I give the password to you and say that take it to Abdullah. And if I want to know that if someone has looked into the password during this transition, we never know, right? Classically, we never know that if someone has used it or not. But in quantum mechanics, in a sense, if you ever look into the system has changed. So I just have to see whether the system has changed or not. So if the system has changed, that means someone has measured it or someone has disturbed it to a certain extent. So that's the idea we are talking about. So how do we see this? It's a same thing. I'm going to do this, but I'm going to give it a small meaning of pretty much repeat what we are doing, right? So this is E1. Keep this static. Put it in a magnetic field. I don't have a control on that. Once I decide that I go through a magnetic field, it will go through. I don't have a choice on 10⁻23 atoms, which one goes through this and which one goes through that. That's happening anyway. I cannot disturb that. What I can do is that once it has gone through the magnet, some of them are up aligned with the magnetic field, some of them are aligned with the magnetic field in the downstroke. I can select. So I can select this or this. So I decide to select on the top, and then I bring it back to E1. Okay. So the only difference I'm playing here is that here I had a choice of E2. I say that I'm going to fix these two. So these two are fixed. So I'm going to keep this always the same, these two the same. Going through a magnet, atoms go through it. Whether I select or not, in principle, should not be a problem. But let's see what happens when I select. So that is one piece here. And so this is one. And the second is just select the other piece. One, two, and this time select the second piece. And there is a third possibility. This is not really a possibility, one is an interpretation that what if I don't do any select? That means I'm allowing both, right? So this is no select. That's a new thing I came up with. And in this case, you would say E1, let's say this is probability amplitude. So this is probability amplitude, that's equal to E1 dotted with G1 and square, right? So G1 dotted with 1. And that's cosine square theta 1 for our purposes with the G1 and G2 in that particular direction with this cosine square theta 1. Probability will be cosine 4, right? E1 square is cosine 4. T2 is E1 dotted with G1, and G2 this time. Q dotted with E1 and E1 dotted with G2 was what? E1 dotted with E1 dotted with, that was sine theta. So that's sine square theta. And you would say the probability here is P2 square. That's sine 4 theta. Now, if I don't do anything, no selection, and I still look for E1. Now, since I have not selected, some of them will go in E1 and some of them will go, if there was an E2, some of them will go into P2. But notice what is the probability amplitude here. So P is equal to, so this is P3, let's say. That's equal to E1 dotted with. Now I have to decide what is the projection operator associated with no selection. If I do not select, some of them can go in this direction, some of them can go in that direction, so I will keep both. So it is G1 plus G2, G2, projection along both directions, I just add up. And that's E1 again. What is this equal to inside the parenthesis? Inside of the parenthesis? 1, right? So it's a completeness relation. That's 1. That's a key here. That's 1. And that makes this 1. So the total probability here, P3 square, is 1. Notice P1 square plus P2 square is not equal to P3 square. This is what is considered measurement disturb the system. We did not do any measurement here. It's the same thing. Notice I just did a, if I were to look at it, this is peeping through, right? Oh, did the electrons go that way or this way? I'm just peeping through what happened to the electron. Here I didn't do anything, the same magnet, all three have the same magnet. The only thing I'm doing is, did all of them make sure that all of them went through or not? I closed the slit here, I closed the other slit, and you would expect that total should be the same. But then when you come back here and look at it, it is not surprising. When you see the mathematics associated with it, it's not at all surprising because there were 2 more pieces there. E2, there were 2 more possibilities there, which we are not considering at all. And that's where it is lost. Right? So when you look at this, after you see through this, that's not surprising. But if you were to look at this in a classical sense, oh, they should have gone through this, either they go here or here. So where are the rest? So that's what makes it surprising. So once you have the algebra, it is not surprising at all. But this is what is called measurement disturbs the system. And the way I did it, it was completely abstract, right? I did not tell you what E1 and E2 were, even though I associated with the Stern-Gerlach setup. You could have taken this to be any operator. I can say, I first measure position, then momentum. First measure position, then momentum, again measure the position. System is disturbed. Just because you went into another basis, the system gets disturbed. If you're in the same basis, it turns out that it doesn't get disturbed. So it matters which basis you're choosing. So to that point, we bring polymatrices. So I should be telling you what polymatrices is. Bit fast for that reason. So we want to do most of this in the context of polymatrices. So the magnetic moment mu is, we said, Q over 2m times angular momentum, let's say J. And J is L plus S, where L is equal to R cross with P. Okay, we will keep that. So we will in fact say, let's consider the case when angular momentum is really zero, so that we want to bring in the quantum effects. And a spin now is h bar over 2, and we set that sigma. That's a vector, simple situation is as a vector, but it is a very special vector in a sense that they are built out of matrices. Whenever we think of vectors, we think of three numbers, right? These are not three numbers. This is an I hat direction times 0, 1, 1, 0. The matrix plus J hat times 0 minus I times 0 and plus K hat times 1, 0, 0, minus 1. We will call this sigma x or sigma 1. This we will call this sigma y or sigma 2, and this we'll call it sigma z or sigma 3. Now, this is a very special representation. This is these are Pauli matrices. Now, every time I say these are the components of something, this is in a basis. So in the basis of sigma z. Now I'll tell you what that means. But before that, I'll keep this as an information. And now, how do we usually work? Notice that Hamiltonian is equal to minus sigma dotted with B. Right. That's a vector. That's also a vector. And now I have to, this should be a scalar, right? How do I build a scalar out of this? Let's say the magnetic field is in a random direction. So this is minus sigma 1 B1. That's the magnetic field in the x direction, or maybe x minus sigma y dy minus sigma z. Oh, by the way, there is a small mistake in here, right? Not a mistake. If I interpret this as energy, energy should be mu dotted with B. So there is a Q over 2m and h bar over 2. So there's a Q over 2m and h bar over 2 that should be multiplied, right? So this mu dotted with B, that is energy, not sigma naught. So that factor is yeah. Right, so the whole thing is Q over 2m h bar over 2. So this is basically sigma dotted with B. Let's say my magnetic field could be in any direction. If it is in a spherical polar directions I choose, this is nothing but I hat times sine theta times cosine phi plus j hat sine theta times sine phi plus k hat cosine theta. So the picture I have in mind is I have x, y, z, and the magnetic field is in random direction. I don't want to choose it in the Z direction. And this is my angle theta. That's my angle phi. So magnetic field is decided by two angles. And these are the Pauli matrices. So let's ask what is sigma dotted with B? That's equal to sigma x times dx. Sigma x dx is, I multiply this in here. So this has a magnetic field. So this is okay, so this is 0. Sigma x times dx, so that is sine theta. It's by dx. That's dx. X plus 0 minus I dy I y 0 plus z. That's how it will look like. I'm basically multiplying this sigma matrices into that. That's nothing but put this all together. So this is dv dx minus I dy. And this dx plus I y. That's minus 3. Each of this magnetic B has a sine theta and cosine theta in it. So B comes out. This Z has a cosine theta in it. And X and Y has sine theta in it. And that is a cosine phi plus I sine phi. That is sine theta times cosine phi minus I sine phi. This is minus cosine theta. That's equal to B times cosine theta sine theta e raised to I phi. Sine theta e raised to minus I phi. That's minus cosine theta. Remember, this is your Hamiltonian, or this involves the Hamiltonian is built out of it. That's your matrix. If I have a matrix, I can have eigenvalues associated with that and eigenvectors associated with that. And these eigenvectors will be decided by what direction is my angle theta. In what direction I choose my magnetic field decides the two eigenvectors. And in what direction I come in, that decides my E1. So this I make a choice. E1 are the eigenvalues of these two vectors in the sense that what direction I choose my magnetic field, that decides my two eigenvectors here. That's my two eigenvectors. And then again, I select which basis I want to work with. That's my third eigenvector. I can fix two of them and keep only one as changing and then do the selection process and do physics associated with that. We'll come back to that. Problems related to how these things change, but in your homework, you will be dealing with sigma method, Pauli method. So that's where it shows up. The idea of a spin is purely associated with the, or it's completely associated with the Pauli methods, or it is captured using the idea of Pauli methods. I'll stop here. 2 minutes of good. Any questions, comments? Did we have a quiz today?
Yeah.
Yes, we did have a quiz.
No,
No, I mean,
No.
today, did I give you a quiz? No.
no.
We should have a break.
Don't understand the relationship between not growing theorem and measurement.
Notice that measurement disturbs the system means that if this is a system, I don't do anything, no measure. Right? If I measure, the probabilities will not add up. Right? So if these two measurements are different, that means something like that. So the moment I keep in, the idea is I just look into the system, I don't think. I'm not disturbing the system, just selection is the measurement here. So just the idea that I make the two beams, like think of double slit experiment, that was popularized using double slit experiment. This is the setup, electrons going in. This, in principle, what is the pattern here? Should not be decided by whether I close this or not. Right, apparently the moment if I close this, then the pattern is disturbed there. Because electrons go anywhere there. Right? So it's very counterintuitive as to just by doing this, I've changed the system. That's why peeping in, so I'm not, I mean, the electrons are going in, no, there's a magnet there, electrons are not, I'm not stopping them. So the system is anyway happening, but just the fact that someone has observed it, someone did some observation changes the system altogether. So that's the idea of measurement. And then cloning is in the sense, if you think of it as a password. So if someone tried to repeat it or try to change the system or copy the system, it has changed the content.
The state is defined by password change.
Thank you, Dr. Sajesh. Oh, sorry.
It's straightforward. It's the basis projections, all that gives it a. Go to the next step. Often we stop here. It's all interference. I mean, or the key here is interference. If we are used to interference, we shouldn't be surprised. Like we first collect the amplitude, then square. Photons are satisfy interference principle. We don't have any significant problem with that. But that's the same thing that's happening here. We get surprised at it. But mathematically, it's very set. That's the way to probably look at it. Hopefully, yeah, all this connects well, and then go back and think about it. Okay.
Thank you, Dr. Sajesh.
Thanks. Yeah.
See you.
So just the exam is today at 2.
Yes, today at 2, I printed here. Today at 2:00. There are only about 20 students, so it should be good. Just come and you won't have to do anything. Pretty sure, hopefully nothing happens. If something happens, you take over.
Ask someone to come for 10 minutes and come for the class.
Yes, it's an emergency situation. Thanks.
Can I end it now?
Yes,
Yes.
you can just, yeah.